Hi and welcome to this video. We're continuing from the example project, the railroad overpass, and now we'll model some low carbon design improvement, focusing on reducing embodied impact. For the first improvement I will show in this model, so this is my baseline model with a total of 812 tons of carbon. Notice that I have limited the lifespan to 25 years with this example, so it highlights, put more emphasis on the upfront emissions rather than operational emissions. And we'll use the scenarios feature in eTool LCD to get started with the improvement strategies. Again, these are focused on reducing upfront emissions or embodied impacts associated with the infrastructure construction. First of all, I will add a new scenario, and this one I'm going to be using an option from the library recommendation template. So replacing cement with 50% fly ash blend in the concrete mix gives me a standard description that I can adjust if necessary. So I'll add this to the design, and I will indicate to the software which is my starting point for the scenario, which is business as usual design. Now start modeling. So it automatically creates a new design for me, and I can start making changes. So I'll use the bulk swap feature for this one. I'll first search for all the concrete elements that I'll apply this change to. So I'll filter the elements that contain concrete. So I'll change the 40 MPa strength only. So I'll select all concrete types and unselect top two. Then I will change the parameter to the material type, and I'll search for my specific mix with the 50% fly ash. Search for 40 MPa unreinforced, and I'm looking for fly ash blend 50%. This, and add this as an improvement. It's giving me a 43-ton savings, very significant savings for this particular example, and I will apply the changes. Perfect. So this gives me a 5.39% savings against my baseline model. And then I'll repeat the same process to model the next improvement. The next improvement, I will use timber, structural timber, to replace beam elements, concrete beam elements. So I can also use an example from the library, building material timber or cross-laminated timber or glue-laminated timber. Again, I can change the description, change the images here to be applicable to infrastructure. As an example, I'll just add this one in and also select the sequence. So the starting point for this one is the previous design. Let's see, following a sequence here, but the scenarios feature as described in the specific scenarios feature video. You can branch recommendations as well. So please refer to that if you need more details. So in this case, I will replace the beams, the concrete beams, with glue laminated beams. So first thing I need to do is I will add the structural timber to my design, add a new template. I'll search for glue lam framing, superstructure, and I need to know the amount of volume of timber, and I have calculated this previously, so I know it's 52.65 cubic meters. Showing you why. I'm assuming the same volume of the existing member, the concrete member, just to simplify the example here. But I'll also add some structural steel to account for the steel connections and support elements. So structural steel in kilograms, and I'll add 5 tons steel. So now I have both templates added to my design. One thing to notice about structural timber is the end of life disposal method, and you can see in this case it's giving me an impact because it's accounting for the benefit the product will have, but it's also taking into account the end of life impact with the full biogenic carbon cycle. So what I'll do as an example, because this is a structural member, it's unlikely to go to landfill. So I'll just change the disposal method from wood landfill to no disposal process, and this needs to be very transparent in the LCA report, and it will then give me that benefit of the biogenic carbon up front. So now what I need to do is go back to my model and remove the concrete beam element. So I'll just search for my beam, and here's the same volume that I entered as a structural timber element, and I will get rid of this template as a simple replacement. Okay, so now I have savings associated with this improvement, take into account the end-of-life disposal method for timber as well, not accounting that actually, so a higher percentage savings for this scenario. Next one, I'll model an example regarding transport impact. What I'll do, I'll simulate a local sourcing of aggregate, so the ballast assumption, optimizing the distance. I'll add a new scenario where I think I have this option as well, pre-configured option in the library, local material source, local sourcing of aggregates to reduce transport impact. So this is giving me some assumptions as well, and I can add to the structure, and I can also add the text. So in this case, I'm reducing the default 175 kilometers. Oh, sorry, 100 kilometers, the new proposed, as opposed to the 175 kilometers in the baseline model. Save this description, and I'll inform the software my starting point for the new scenario. And I will make a change using, so this one I'm just changing one specific template. I could have used the bulk swap and gone through the transport, material transport options, but because it's just a simple change, I'm going to use the template directly as another option for making the changes. So I'm going to search for my ballast template. So within the template, I navigate to the material itself, ballasted track, the amount of material here, and then I'll make the changes regarding the distance. So what I'll do, I'll add another articulated track, 100 kilometers, and I will remove the existing one. A simple change just to show how transport optimization can be modeled in eTool LCD. And back again to my scenarios. So this is less significant savings, although every improvement is important to achieve that net zero infrastructure, the net zero carbon infrastructure performance as well. It's really important to add all efforts to reducing embodied impacts. So following from the transport optimization improvement, we'll now model waste reduction improvement. So I'll create a new scenario. I'll stimulate an improvement in reducing the concrete waste. Now set this as a material improvement. I will change the factor of safety to 0. I'll create a new scenario and put a basic description here, changing the concrete waste factor from 10% to 2% following waste management plan. So this is now a new scenario. I will inform the software the starting point again, following the sequence. And I'll again use the bulk swap feature to make changes to construction waste factors. So first, search for all the concrete elements. And you can see in this waste factor column, they all have default 10% waste factors. So I'm going to select all the concrete elements and change the waste factor percentage to 2%. This is giving us a 9 tons of carbon reduction. I'll apply the changes. I'll check what percentage savings represents. 1.13% savings against the baseline model. And I will also add another scenario where we're changing the concrete disposal method. So it's concrete downcycling from landfill to concrete, crushed concrete to be used as road base, for example. So it's 0% safety as a new scenario. Concrete downcycling. Changing end of life disposal method from landfill to recycling. Save that. And then I also tell the starting point of this. And then what I'll do with these, I'll also use bulk swap because I can change the construction end of life, actually the end of life method for the concrete elements. Again, I'll find all the concrete elements. They have inert waste landfill as a disposal method. And what I'll do, I'll just select them all and change the disposal method to recycling concrete. Add this to my model. Again, it's giving me 9 tons savings. Apply this change and see what percentage impact reduction provides the model. A 1.1% impact reduction. So next one here will be focused on A5 impacts, so construction impacts. So I'll add a new scenario and I'll call it reduced construction fuel consumption. I'll call this other improvement category, zero factor safety, create a new scenario, and I can paste my standard description into this one as well as an example. In this case, crane fuel consumption is a dominant impact in equipment use. This can be improved with a bunch of different strategies, reduce setting minimal fuel efficiency, fuel use targets for the contractors, ensure operators are trained, and also reduce idle time with properly matched equipment, a best practice, and also preparation and site access. There's other high risk or less common strategies will also address this impact, including electrified or biodiesel or hybrid powered equipment. So in this scenario, we're assuming a 20% reduction in the number of hours of crane equipment used, just as a proxy for the fuel reduction. So I'll save this and I'll show a different method of at the starting point for the concrete downcycling. Save this as well and apply the changes in my equipment runtime. The way I can do this is by using bulk slot feature again, very handy, but using a different tab here. So navigate to the equipment and I'll filter equipment that contains crane. So I have multiple use of crane. The most significant one is the erection and fixing of precast columns and beams. So the majority of the time is going to these two. So I'll just use these two as an example. And then the parameter here will be the quantity. It's actually the quantity is the number of hours. And I'll change the percentage to 80%, which will apply a 20% reduction. So this is significant savings, 17 tons of carbon in fuel reduction. Apply this change and have the new scenarios created. So this has given us some examples of improvement strategies to reduce embodied carbon. Again, very basic, but gives you an understanding of the software functionality and also how you compare the different strategies. Then you can run a cost analysis in conjunction to understand, the amount of dollars invested per ton of carbon saved and focus on the key improvement strategies. So stay tuned, we'll now run another set of improvements focusing on operational carbon as well as functionality improvements.